Okay. And hopefully everyone will get an email link. If not, I will send you a link later, Daniel.
Yep.
Okay. I'll just quickly introduce you. As a little bit of background, I was on Facebook a couple of weeks ago and happened to notice a very interesting article posted by one of my Facebook friends, Daniel, about quantum satellite communication. I don't know anything about the topic, but I thought it would be wonderful to learn more about it. Then I realized that these days seminars are online, and maybe we could be lucky enough to get Daniel to talk to us. And he has indeed agreed to tell us about his work. Daniel is a senior lecturer in the Department of Physics at the University of Strathclyde in Glasgow. He is a member of Computational Nonlinear and Quantum Optics Group, which must be really advanced because I can almost not say it. And his research interests include fundamental aspects of quantum theory, quantum engineering, quantum computation, and quantum space science and technologies. Prior to Strathclyde, he was a research fellow at Sydney Sussex College and the Department of Applied Mathematics and Theoretical Physics in the University of Cambridge. He was also previously associated with Oxford, weren't you, Daniel? I don't see that in your bio here.
Sorry?
I thought you were at Oxford too for a while.
Yes, I did my my doctorate there.
Ah, yes. I wonder what it is like to go from one of those to the other, since they seem to love each other greatly.
Well, they're more similar than different.
Oh, good to hear. I met Daniel way back when he was studying in Perth here at the University of Western Australia. He studied physics and mechanical engineering and did some very interesting things there, as all the physics type people do. He has completed the doctorate at the Centre for Quantum Computation, Oxford. Yeah, there we go, I missed it. And now leads the Quantum Research CubeSat program called Quark, amusingly enough, and is the Chief Scientific Officer of the Responsive Operations for Key Services mission, led by Craft Prospect Limited. He's also co-investigator in the research he's going to be talking about today on quantum technology hubs in quantum communication. That is a mouthful. Okay, Daniel, I've talked enough. Please, over to you.
All right, thank you. I'm very happy to speak to you today. It's some of a virtual homecoming, I guess. As Hannah said, I did my undergraduate at UWA a long time ago. Haven't had the opportunity to come back all that often, but it's nice to be here. So I just wanted to, obviously, I need to acknowledge the people or organisations who have supported my research. So the various people in the UK have supported the UK Space Agency, of course. The satellite applications catapult. Contrary to the name, they don't actually use big catapults to launch satellites, but they try to help develop satellite technologies and actually apply them to real world problems. I work with the Scottish Centre of Excellence in Satellite Applications and lots of companies, and I am mainly sponsored by the Quantum Communications Hub as part of the UK National Quantum Technology Programme. So enough of that. So I just want to start it off by talking about why do we want to do quantum physics in space, or why space a useful environment in order to try to do physics experiments, quantum physics experiments. Well, one thing is that the Earth is a very noisy place. So when you're trying to do very sensitive experiments, we want to get away from vibration, electrical noise, RF noise, and heading away from the planet actually can help reduce man-made noise, whether it's vibration or electromagnetic noise. So that's very useful, especially when you're trying to do very sensitive measurements. A lot of experiments benefit from trying to conduct them over very long distances, so long sight lines. Obviously, the Earth, it's curved, so it's very hard to actually get a straight line distance over, more than a few kilometers. It's very difficult. If you want to go, say 100 kilometers in a straight line, send light over such distance, you have to go on top of mountains and try to find another mountain you can send signals to. And obviously in space, when you're in orbit, you're in a microgravity environment. You're in free fall, so you don't see you don't see you don't feel the effects of gravity. I mean, there is gravity, but you are in free fall. So effectively, you're in an inertial frame. And a lot of experiments benefit from not having to support your experiment from the effects of gravity. Effectively, you can have something which is freely falling and you don't need to support it. Also, obviously, in orbit, you've got high velocity. So if you're trying to look at relativistic effects, then it is very hard to see those effects with the kind of velocities that we can actually generate on Earth. And if you're looking at general relativistic effects, then obviously we need to go to different gravitational potentials or areas where the curvature of space can be seen, and going into orbit is one way of doing that. So for a long time, space has been a very it's been an environment which we would love to operate in and do lots of experiments, but it is very challenging. So what kind of things do we want to do in space in terms of quantum theory, quantum experiments, fundamental physics? Well, you may have heard about the gravitational wave detection gravitational wave observatory, LIGO, Light Interferometric Gravitational Observatory, which actually has several interferometers on the ground. But to get even more sensitivity and to look at very low frequency gravitational waves, we will need to go into space. And so LISA is such a proposal where we have a very, very large baseline, million kilometers compared to only maybe 3 kilometers on the Earth. We can look at trying to test quantum theory in terms of whether quantum entanglement can survive over very long distances by trying to send it between satellites or between space and ground. And we can look at whether the very counterintuitive effects of quantum theory, such as measurement and collapse, whether those things persist when we have a long time between, for instance, making a measurement and later on trying to erase that measurement, so such as in the Wheeler delayed choice experiment. Obviously, if we can go into a microgravity environment, we can let things effectively fall for indefinitely. So this is very important for looking at how things like Bose-Einstein condensates or BECs evolve. On the Earth, when you create a BEC, normally you have to use different fields, such as optical fields, to levitate it against the force of gravity. Now, those fields that you're using to hold it against gravity, they affect the BEC itself. And we can't let it, it can't evolve naturally for longer than, say, a second. That's the time it takes for a BEC to fall the distance from the top of the experiment in your lab to the bottom, to the floor of your lab. Whereas in space, you can let it basically expand very slowly over several seconds and see whether you can see new quantum physics in a BEC. In microgravity, also, we can look at much larger objects, not just simply these very cool atoms, but we can look at macroscopic objects, things like nanospheres, or even gram-sized objects, and see whether quantum effects can be seen at that level if we look at it long enough in free fall. There are other things we can look at whether gravity, whether it follows precisely an inverse square law. There are different theories of physics which predict that gravity, Newtonian gravity, doesn't actually follow precisely a 1/r² dependence. And if you could go to space and look at the motion and accelerations of objects over a long period of time at slow speeds under free fall, then you may be able to detect these tiny differences from the 1/r² potential. We can also look at whether things fall at the same rate. So Galileo's famous experiment by dropping, well, he actually didn't do this, but the apocryphal story of him dropping heavy and light objects off the Leaning Tower of Pisa to see whether they fell at the same rate. Well, we can do that to a much higher precision in space and check whether heavy objects and light objects actually fall at the same rate. So for more practical reasons, we can look at exploiting space for quantum technologies. So what I work in is satellite quantum key distribution. This is where we try to use the laws of quantum physics to secure communication against any unauthorized eavesdroppers. We can use it to distribute entanglement. Quantum entanglement is going to be very useful for networking quantum computers in the future. So when we develop these satellite quantum key distribution networks, they could be then developed further to actually implement the quantum internet. Putting very accurate clocks in space is very useful. In fact, GPS relies on having very accurate clocks in GPS satellites. And if we could increase the accuracy of these clocks by using more advanced quantum techniques, then we could potentially revolutionize navigation, timing, positioning. By measuring gravity around the Earth by using quantum sensors, we could actually build up very sensitive maps of the mass distribution of the Earth, which is very important for a lot of applications. Not just say oil and gas, but for environmental monitoring, for understanding how the oceans circulate. We can even look at potentially atmospheric changes, and also just getting a much better idea of what the Earth looks like beyond just a few meters below the surface. There's very little information about actually what is just below our feet. Also, we can use quantum sensors obviously to measure things like electric and magnetic fields, also accelerations and rotations very precisely, which is very useful for instance, spacecraft navigation. So I'm just going to go a bit more quickly through some of these applications because I want to get towards satellite quantum key distribution. But with clocks in space, we can as I say, GPS, global position and navigation systems, they rely on very precise timing, and if we make them better, we can synchronize them across the globe. Then there are a lot of applications. I mean, finance, they rely on very precise timing. Standards, the internet, 5G, they all can benefit from better clocks that could distribute a time signal across the world. We can do lots of quantum experiments just to test our understanding of how the world works, how physics behaves. There are novel effects which have been predicted about how entanglement works in curved space-time in orbit, and how it changes when you try to move your objects which are entangled. So that could be tested in orbit. BCs, or cold atoms, are actually they're a basic experimental tool by which we could possibly test these effects. BCs, Bose-Einstein condensates, they're extremely cold atoms. They're maybe nanokelvin or even colder, and because they're moving so slow that their quantum uncertainty of the individual atoms, they are larger than the actual distance between the atoms. So the atoms, they lose their individual identity. So these atoms that are very cold and close together, they behave as one gigantic atom, and hence all of the effects that we could measure using individual atoms, they're greatly enhanced. in this quantum state, in the Bose-Einstein condensate. So this allows us a very sensitive probe of different effects. And we could use that in space, because in space we can generate these things, we can let them evolve freely for a long period of time, and we can then also couple that with quantum entanglement in order to test quantum mechanics at large distances. The Einstein equivalence principle, this is what I was talking about in terms of dropping different objects and seeing whether they fall at the same rate. This has been done on the Earth in a way, and but to get really high accuracy and try to show deviations from perfect identical accelerations of two different objects, you need to go to space and let objects fall for months or years at a time and see whether they actually do differ in their accelerations. So there are various ways of doing this, and using cold atoms and quantum systems may be one way of doing it. Gravitational wave detection. So I talked about LISA, which is the this large interferometric space astronomy telescope for looking at very low frequency gravitational waves. We can put two quantum clocks basically in orbit, and a gravitational wave will affect the time that these two clocks will measure. And if you can compare the time of these two clocks, then if one clock runs slower and then faster than the other one, then that may be a signature of a gravitational wave passing those clocks, and the local distortions of time affecting the local rate at which the time passes. And we need very accurate quantum clocks in order to do this. Macro is an experiment which is basically trying to look at Schrödinger's cat, right? Trying to show that large objects can actually exist in this weird quantum superposition of one state or another state. Obviously, it's a bit hard to actually launch cats into space, so we're just using very, what are called nanospheres. These are little beads of glass silicon that we can silica that we can cool down very, very cold, and therefore we know exactly where they are, and then put them in a superposition of being in one place or another. And if that's true, then we can measure this effect and show that objects that you could actually see with your naked eye, these can actually behave in an intrinsically quantum manner and actually be in this weird quantum superposition. We have to get into space because we have to get away from the noise of the Earth. We have to be very cold, and we need to have a very stable environment. Now, we're getting towards the area which I'm mostly interested in, and what I'm mostly working on, which is quantum communications. So Space Quest, besides being the name of a movie, was a proposal to try to send quantum entanglement from the International Space Station. This was originally maybe around the early 2000s. This was proposed, and it was proposed in Europe, and unfortunately, it wasn't quite funded because it cost a bit too much. And over the years, it's evolved. But the basic idea of taking quantum entanglement, quantum signals, quantum optics into space and try to then do long distance experiments. This was later taken on by various groups. Instead of using the International Space Station, you could, instead of sending light signals from space, from a satellite down to the ground, it's a bit cheaper to do it the other way around. So for instance, if you have a ground station, so here we've got what's called the Matera Laser Range Finding Observatory. This is a telescope in Italy. You can send light pulses from the ground and bounce it off a satellite. Now, there are these satellites which have these retroreflectors. So these are basically huge mirror balls in space, and it will reflect a laser beam which is shone on it directly back to where it was sent. So what you can do is that you can basically create a quantum superposition of light, send part of that up to the satellite, and because this distance is so long, it's several thousand kilometers, there's enough time that in the time it takes for that signal to come back, you can actually decide to do one sort of quantum measurement or another quantum measurement. And one of the consequences of quantum theory is that effectively you are delaying your choice of what kind of quantum collapse, in a sense, you are going to impose on the quantum system that you've generated. And you can do this after the point at which the quantum system could possibly know or choose to behave one way or the other, behave like a particle or behave like a wave. So this kind of experiment really demonstrates that this particle wave duality or other similar kind of quantum characteristics and properties, they are not in a sense predetermined by state preparation or any of the choices that the experimentalist does prior to the measurement, because what we're doing here is we're making the measurement at the very last stage. The quantum system can't really choose whether it behaves like a particle or a wave, until the last minute when you actually do the measurement. And we require a very, very long distance that we can send these light signals in order to allow us that time in order to make that decision independently of the quantum system, if we were to believe that quantum mechanics was in a sense deterministic. So I'm just going to run through some milestones in the last couple of years which have really been exciting in terms of taking these ideas of what we could do in space and actually putting it into practice. So one of the big achievements in the last couple of years was the first Bose-Einstein condensate in space. Now, normally, if you try to create a Bose-Einstein condensate, you will require a whole lab full of physics experiments, lasers, optical tables, lots of optical equipment, and you have to get it to space. You need to cram a room's worth full of equipment into something which is size of a suitcase or a large suitcase, basically. Now, the BCs actually they're quite recent. They won the Nobel Prize in late 20th century. I think it was, I can't remember, it was 90s perhaps. So they're actually not that old in terms of how recent they were first produced, and to actually put them to space in this is an unmanned rocket. This is so this experiment Maius in January 2017. They put everything into this rocket, actually into a small little bit of this rocket. Most of it's actually rocket fuel, and they sent it up on a what's called a suborbital trajectory. They sent it up. They had about 6 minutes of microgravity or free fall, and in that short period of time, they were able to do many different experiments, totally automated. I mean, there's no room to put a PhD student in this. And so that they were able to automate everything and show that they were able to create these BCs as well as they could have done on the Earth. Now, very recently, NASA caught up. So very recently, NASA reported that on the International Space Station, so this is in orbit now, this isn't on a short trip to space, they were able to make BCs in what they call the Cold Atom Laboratory, or CAL or CAL. Obviously, if you can make it in orbit, you can do more experiments. You can have potentially a much longer free fall, not just 6 minutes, but indefinitely, or however long the ISS is going to remain in orbit. But that was what was a really major achievement, to just show the steps one could actually take to miniaturize what would normally take a room or two rooms full of experiment and cram it into a very small space and get it to operate in very harsh conditions. So what do I work on? Well, I'm working on what's called quantum key distribution. And you may have heard or even been taught about quantum computers. And one of the key things about quantum computers is that it can run a particular algorithm called Shor's algorithm, which can break RSA or RSA encryption. And RSA encryption is basically one of the most most used algorithms in the world, because it underlies a lot of the internet, a lot of the encryption which happens in the internet. So if we can build a big quantum computer, and people are working very hard to do that, then it would basically break the encryption or the fundamental method by which the internet is secured. It can also break elliptic curve cryptography, which is the other main public key encryption method. Now, this is obviously a bit worrying, because public key encryption is very, very useful, and it solved this fundamental problem, which is called the key distribution problem, and that how do you get secret keys, which you use in order to encrypt messages, how do you get it to people so it's secret in order to generate secret channels. Now, obviously, this is the chicken and egg problem. If you don't have a secret channel in order to distribute your keys, then you can't create a secret channel. And public key encryption was one way of getting around this problem. But if that's broken by quantum computers, then we have a big problem on our hands. So quantum key distribution was actually invented in 1984. So this is predating Shor's algorithm in 94. But it solves the key distribution problem in that you can generate a secret key between two parties that have never met. Well, technically, it's key expansion. It expands a small shared secret key into an arbitrary long secret key. And this is a method by which one could secure certain types of links, highly sensitive links, against quantum computers. And so this has been of great interest to things like people like banks, financial institutions, perhaps healthcare providers, securing private data, governmental communications, all sorts of highly sensitive information which we may want to keep secret. If it's being sent now, if someone basically stores the information, the encrypted information, when a quantum computer is eventually developed, then it can go back and decrypt all that stored information. So information that you send now, which you may want to be kept secret for decades. I mean, for instance, your health information, your medical records, in principle, that should be private till the day you die, or even beyond that. So that kind of information, you may need to secure it now, even though a quantum computer doesn't exist at the moment. If it does exist in the time scale within which the information that you're transmitting now still needs to be secret, then you need to start sending that information at the moment in a way that is resistant to attack by quantum computers. So this is called forward security, and QKD at the moment is about the only way that we can ensure forward security against quantum computing attack. So how does quantum key distribution work? Well, so we've got Alice here. So the two protagonists is going to be Alice and Bob. Bob the Builder here, Alice in Wonderland here. And we have a satellite, and the satellite sends a stream of single photons to Bob. Now, these single photons, in their polarization state, so the electric field direction, they can encode either zeros or ones, but we can encode a zero in two ways. Either we can encode it as a vertically polarized photon or as a 45-degree polarized photon. We can send the 1 either as a a horizontally polarized photon or a minus 45 degree or an anti-diagonal polarized photon. Now, because these are single photons, they are very difficult to look at, to measure without disturbing it. All right. So when Bob does a measurement on whether it's either vertical or horizontal, or whether it's diagonal or anti-diagonal, he destroys basically the quantum state. So he makes the measurement, and that information, which was whether it was in this state or this state, or this state or this state, he's one go at it, right? And the other thing is that he can only choose to figure out whether he gets these two outcomes, say vertical, horizontal, or anti-diagonal, or diagonal or anti-diagonal. Now, if he chooses to measure in this basis, but he was given, say, an anti-diagonal state, then he won't get an anti-diagonal result. He'll get one of these two results at random. So if Alice sent, say, an anti-diagonal state, she sent a 1 in this state, and Bob chooses to measure in this basis, then he actually gets no information about whether Alice sent a 1 or a 0, right? So only when, say, Alice sends a 0 or 1 in a vertical horizontal basis, and Bob chooses to measure in the horizontal vertical basis, does Alice and Bob actually get to tell each other anything, in a reliable manner. If Alice sends one of these two states and Bob measures in this basis, then that's useless, and they discard that attempt at trying to send that bit. So this is discussed. This is all public discussed. Alice basically says, I sent one of these two states, or I sent one of these two states, and Bob says, I measured in this basis, or I measured in this basis. They don't actually say what was sent. They don't tell you, they don't say to the world whether they sent a 0 or a 1. They just merely say, I sent either this or this, or I sent one or this or this. And Bob says, I measured in this basis or this basis. So if no one was listening, if no one was actually trying to intercept the single photons, but they just knew the basis that was sent and measured in, they would not know the actual value of the bit being sent, right? So in this way, in the ideal perfect protocol, Alice and Bob now would share a randomly generated key. So Alice generates the 0s, the 1s randomly. Bob would know exactly what Alice sent, a 0 or a 1, and no one else would know it. All right, so that's the secret key. Right? But Eve could try to eavesdrop on these single photons. She could try to detect whether Alice sent one of these 4 states, right? Vertical, horizontal, diagonal, anti-diagonal. Now, if Eve tries to do that, any measurement she does will either, right, reveal very little information on the state, or if it did reveal information about the state, it would disturb the state so that when Bob and Alice compare a small subset of the results, they were able to detect that there were errors, right? So when Alice sent a 0, say a vertical, and Bob measured in this basis, a vertical horizontal basis, maybe sometimes he would have gotten the wrong result. He would have got the 1 result instead of the 0 result. So by doing a sampling of a subset of all the signals received, Alice and Bob can detect whether Eve tried to eavesdrop, right? So in this way, they can either certify that the channel was secure. If they do detect some errors and they assume that this is all due to an Eve trying to eavesdrop and measure the signals, they can then do what is called privacy amplification, and they can take the amount of actual secretness in the information that Alice and Bob have, and distill that, and removing any information that Eve has on the string. Right. So it's not just about detecting eavesdroppers. It's also about quantifying the amount of information the eavesdropper has about the secret signals that Alice and Bob are sending, and also being able to remove that that non-secret information from what Alice and Bob have. Right. So that's something that is often lost in descriptions of QKD. All right. So QKD. Now this has been developed, and actually it is there's a small industry in the world producing QKD systems, both the transmitters and the receivers, and most of them operate using optical fiber. You plug in your transmitter at one end of an optical fiber, you put your receiver on the other side. You can't have any can't have any optical repeaters in the way. It has to be like one single unbroken channel. So typically one single fiber. You can use passive optical switches, but no active switches. But the range at which you can actually do this is limited. It's because optical fiber has this exponential loss. It's typically 0.2 dB per kilometer, but over 100, over 200 kilometers, even the small loss becomes a large loss because of the properties of exponentials, right? We all know about the properties of exponentials, hopefully by now. So even a small amount of loss in 1 kilometer becomes a large loss over 100 or 200 kilometers. So we can't really do QKD using an optical fiber for certainly not over 1,000 kilometers. And typically, if we want to connect countries or continents, we need to be able to transmit these quantum signals over much farther distances. You could try sending it over the air through space, but because of the Earth is curved, you can't really do it unless you go very high. So the longest range that's been done on the ground has been between two mountaintops in the Canary Islands, and that was 144 kilometers. And that was simply just to get above the curvature of the Earth, and also to reduce the amount of atmosphere in between those two places. So satellite QKD, it takes the idea that you can use a satellite which can see a large bit of the world at once. And most of the time, when you send a light signal from a satellite to ground, it's going through vacuum. It's not going through anything that will absorb it. So all that matters is, say, the divergence of the light beam, and that's diffraction limited, and it's basically a 1 over r squared. 1 over r squared diminishes a lot slower than exponential, right? Over 1,000 kilometers, a signal may decay via 1 over r squared by maybe 60 dB. But if it was for a fiber, it would maybe be 1,000 dB, right? Or 200. So we can use a satellite to send quantum signals very far between two different places of the Earth. Now there are two methods of doing this. One is called untrusted node. So up here we've got a single satellite. It sends entangled photons down to two receivers, A and B. Now, this is a slightly different protocol to what I showed before, but effectively it does the same thing. Alice and Bob can make measurements on the quantum signal sent by the satellite and confirm that the secret key that they measure is actually truly secret. And if it's not truly secret, they can make it truly secret by doing privacy amplification. This is very difficult. Doing a simultaneous downlink of entangled photons is actually very difficult, and we'll see later just how difficult that is. Trusted node QKD uses the satellite as a trusted courier, where you do key distribution, say from the satellite to one receiver on the ground. the satellite goes to another point on the Earth, creates a separate independent secret link, and then the satellite can basically connect A and B together by broadcasting a hash function of the two different secret keys. And this is scalable, and it's you can create big constellations of this kind of trusted node QKD network. But you do need to trust the satellite. Now, if you build and launch that satellite, then that's probably a fair assumption. But we want to get to the stage where, in this case, in this untrusted node situation, anyone could operate the satellite, because Alice and Bob can verify that what the satellite is actually sending them is actually what it should be sending. So this is why you don't need to trust the satellite in this case. So we're trying to head towards this kind of situation. And because we're sending entanglement, this entanglement later on could be used to actually network quantum computers. So that's where the trajectory of the research is going. We're going in the short term. We're actually going to just try to build this trusted node, and then later on try to do untrusted node. So basically, this area of research had its wake-up call when China launched the Quest mission with the Messias satellite. This was a big satellite. It was about 650 kilograms. It was launched into orbit in 2016, and over the next couple of years has generated a huge amount of excellent experiments and results showing that this is actually possible. So it's done this experiment of sending entangled photons down to two separate places on the Earth at the same time, and that should be over 1,200 kilometers, which is nearly 10 times greater than the previous record of 144 kilometers. I was able to do teleportation between the Earth and space, and was able to do this trusted node QKD, linking up Europe, Austria, and China. So this has spawned a global space race to try to catch up to the Chinese. So there's a lot of different missions around the world being developed. This is actually an old image. There's Quark, which I lead in the UK. There are various commercial projects which are being sponsored by the European Space Agency. There's a separate European Space Agency, European Commission project to try to do entanglement-based networking throughout Europe using space as well as ground networks. And there are several CubeSat projects which I'm involved in. What is it about space which makes a big problem? Size, weight, mass, power, that all costs you a lot of money to launch anything big. So you try to make things as small as possible, run with as little power as possible, try to make it fit with the small volume as possible. And that's very challenging to try to get these, what are, traditionally, lab experiments taking up, whole rooms and cramming it into something the size of a loaf of bread. Have to use very little power, and it has to get up into space. So it has to survive launch. It has to survive the radiation in space, the temperature swings, and obviously vacuum, and it has to be survive launch. Traditionally, this process has been very expensive. So the Hubble Space Telescope, $1 billion. It was a decade late, 10 years late. But now we can actually launch very small satellites, say CubeSats. They only take maybe months to build. If you're very, very quick, you could get it up, within a year if you signed up to a launch provider. And they basically hitch a ride into space. They do what's called launch ride share. So when a big satellite's being launched, you can actually say, well, can I hitch a ride with my small satellite? And obviously that's a lot cheaper than your own having to pay for your own launch. So there are big satellites, there are medium satellites, mini satellites. I'm operating with what are called nanosatellites or CubeSats, and they're around 1 to 10 kilograms and roughly about $100,000, roughly in that region, compared to $1 billion for a large satellite. There are even smaller satellites. There are these CubeSats, which are literally just PCBs plugged into space. The new space revolution is basically allowing us to launch these small satellites. So it's a new way of thinking of how to develop space systems. Instead of taking decades and billions of dollars, we're trying to do things in months or a few years and launch on a very small budget. Maybe launch on small rockets, not big rockets. This is an Australian, Gilmore Space is an Australian rocket developer, actually. And they're all around the world, these small rocket companies. There's Rocket Labs in New Zealand is actually one of the most successful small rocket providers. So this is what a CubeSat roughly looks like. It's a fully fledged spacecraft. It has communications, it's got onboard computer, it's got solar panels to generate power, it's got usually a way of controlling the way it points, an attitude control system. This is the UK's first official CubeSat. This is called UCube-1. I work with Steve Greenland here, who was the systems engineer on this project. And he's actually putting it together, and this was launched a couple of years ago. You can buy them off the shelf, so you can go to companies and say, I'd like a satellite, and they'll provide you one. And this graph just shows you why they're just so cheap compared to normal satellites. This is basically the cost of satellite missions compared to their size and power. And there's this, almost, very good fit. And basically, we're operating down here in terms of cost compared to mass and power. So, we're orders of magnitude cheaper than say the Hubble Space Telescope or LISA. So we can do things much faster, much cheaper, and it's a way of gaining experience of developing space systems. Space is hard, and getting the knowledge and experience is very valuable. So the faster you fail, the faster you learn. And so we can do these missions. We can do several missions, not just one mission, and learn as we go along. Obviously, there are limitations. We can't do everything with them, but they're actually good stepping stones to building larger satellites. Launch costs, they're actually quite reasonable. We can actually afford one of these launches on a research budget, on a moderately sized research budget. And their launch is going up all the time. So if you want to go into space in the next couple of months, then there may be a launch that you could actually put your satellite on. I won't go into that much. This slide is about, we want to make sure that we don't create a space debris problem. So we want to keep in low Earth orbit. I'm just going to skip some of these and just get to the quantum CubeSats. So for a bit more information about how CubeSats can be used for quantum science, there's a review article here in Contemporary Physics that I wrote with a few co-authors, which go into a lot more detail about this. Now, CubeSats, why do we want to use CubeSats for quantum key distribution? Well, this was a very, what we thought was a quick way of getting quantum experience in space, getting the experience, finding out what we need to do to design quantum experiments to work in this environment. So, the challenges I've said before, how to make things operate with very little power. We've had to do it in collaboration. It's quite a friendly community, so it's nice to be able to work with people around the world in this area. So I've been working mainly with the Center for Quantum Technologies in Singapore. So Alex Ling is the person who I work there. I basically said to the CQT in 2009, on the 40th anniversary of the moon landings, I said, why don't you set up a space program? And they said, that sounds like a good idea. So, the next year, within a year, they hired Alex to start up this program. And preliminary aim was to actually produce entangled photon sources which could operate in space. We need to make them very small, very rugged, and operate with very little power. And this is what we have achieved. So basically, we want to take what is on a huge optics table and make it into something that fits onto the palm of your hand. Literally, this is something that it's about 10 by 10 by 3 centimeters. We've had a few experimental steps along the way. We've done balloon testing. So this sort of simulates sort of the low pressure, low temperature environment, and really means that you have to produce something that can work autonomously. You can't send up a PhD student to tweak the experiment if it's not working properly. This was the collaborators in Switzerland. So this is our first launch. This is the SPEX-1. The SPEX-1 was the name of the experiment, which was put on the GOMX2 CubeSat. So this is 2014. This is the launch. I don't know whether this will, hopefully I don't know whether it will actually show the video, but this is our first launch. Oh, yes. I still cringe when I watch that. Anyway, we did not go to space that day. It wasn't all bad in that, despite that huge explosion, the cargo capsule survived. It was recovered. We got our satellite back and booted up. And the experiment inside worked flawlessly. So despite that massive explosion, our source that we created was operated flawlessly. So it showed that we were able to produce a rugged quantum device. A year later, we launched the next satellite, and that worked. We've got good results in orbit. It's still up there, I think. Oh no, it may have deorbited, but. And then recently, last year, we launched our third satellite, which basically was the culmination of all of this. And we demonstrated that we're able to produce entangled photons in something literally that big. So this is actually a picture of it being deployed into orbit from the International Space Station. It's still up there. It should probably be up there for about another year or so. And we're producing entangled photons. We send a single blue photon through some non-linear crystals, and these non-linear crystals, they convert the blue photon into 2 infrared photons. And these 2 infrared photons, they're entangled in their polarization degrees of freedom, and then we detect that entanglement on board the satellite. So later on, we want to take one of those photons and send it towards the Earth, so that one photon will be measured on the satellite and the other photon would be measured on the Earth, and then we would try to demonstrate that we have these quantum correlations that can exist between the satellite and the Earth. So in the UK, in Europe, we've been developing our own CubeSat program. So I was leading this consortium to try to build and deploy a satellite to do this transmission of entangled photons to ground. That evolved into a UK program, Quark, which I've been running, and we've been building experiments to try to build this method of transmitting these single photons to ground. We've done a lot of system development. This is roughly what will look like. This is about 30 by 20 by 10 centimeters, so slightly bigger, but still something that you could carry on your hand luggage and on a plane. This is a system block diagram of what the satellite would look like, what the OGS, the optical ground station would look like. A lot of different systems that need to work together. This is sort of block diagram of the satellite systems itself, and this is the payload, which has the quantum source. It's got a whole bunch of optics to try to steer the single photon from the orbit down to the ground. This is a very challenging problem. How to send a single photon 1,000 kilometers from a tiny satellite down to a telescope, which is only maybe 50 centimeters diameter. So we're using these micro mirrors, which can be controlled very precisely, and they can point in a very precise direction. We need to have space telescopes, so a lot of design on that. That's quite challenging. And we're building up towards actually a satellite. So this is the satellite chassis itself. This is the structure. And then within it, we will put things like a telescope and this optics box, which does this beam steering itself. This is with conjunction with a company called Craft Prospect. They're going to try to launch this in about 2 years' time. So we're working very hard to build this. We've got a quantum source. So this is the source which generates those single photons. This is about maybe this big. So here's an early prototype, 3D printed structure for it, an even earlier version here. And we are developing our own optical ground station. So we need to receive those photons and measure it. So we've got this telescope. This is actually our telescope. It's small enough that we can actually drive it around on the back of a trailer. And this is what we plan to do. The UK, it's not known for its sunshine, so we need to go around and hunt for where there is going to be clear skies during the night and set this up and actually talk to our satellite. Anyway, I'm getting to the end of my time, so I'm going to just talk very quickly about the future. The future is basically we need many, many satellites in low Earth orbit in order to generate a service. We need to be able to cover every bit of the Earth and actually allow this quantum communication. There's a lot of different things we can do. We can, ultimately, we want to do the quantum internet, global entanglement distribution. This also helps with fundamental tests of physics and also deep space quantum communications. This could be very useful in increasing the amount of data we can actually get to and from spacecraft, in the outer solar system. So that's my team. Huge thanks to all of those people who have worked on this, and thanks for your attention.
Well, thank you very much, Daniel. That was very detailed and highly interesting. I do hope this nuclear explosion is not meant to be indicative in any way. Is it actually nuclear?
No, that's the first launch. That's the first launch, yeah.
Ah, so it's all good news then. Okay. Yeah, I thought, well, what are you trying to bring across with that picture? Okay. Look, thank you very much for that. You still have some time to take questions?
Yes, I'm very happy to take questions.
Very good. If anybody would like to ask a question, you can unmute yourself and ask a question that way if you like, or you can type in the chat and I'll pass that question on to Daniel. Does anyone have anything they'd like to ask? Well, I'll start it off then, because you did mention that basically one of the things that's to come is to have a network of these satellites in orbit. Is that actually needed for proper commercialization, or can you do it with a rather limited amount of satellites?
That's a very good question. So initially, QKD is going to be a niche product. Therefore, the people who may need to use it is going to be limited. So that might be able to be serviced by a few satellites. In fact, there have been companies who've been looking at launching maybe a single satellite at start and then building up their constellation and service as more customers are built up. So actually, the first commercial missions to be launched in a few years' time, maybe two years' time, they're aiming at a very small pilot program with just a few satellites. But eventually, if this becomes ubiquitous, then I think we're going to go the way of these mega constellations like SpaceX or OneWeb.
Okay, well, that sounds promising, because that means we don't have quite as long to wait. And my next question was going to be how long, and you've said a couple of years. I have a question that's not directly related, if you don't mind. When I talk to my students about the quantum communication and breaking the in quantum computers, breaking encryption, all that sort of thing, they of course ask me, well, when do I think it's likely that somebody will start breaking quantum communication. My answer is always, actually, it's entirely possible it's already happened and we wouldn't know about it, but that's as an amateur. Do you have a more official answer for someone working in the field?
There's a lot of speculation. I think it's most likely that there isn't a secret quantum computer out there breaking codes at the moment, because I think that the engineering effort that is happening and the level of engineering effort that's required to do so, that is being done, by IBM, by Google, by Microsoft. That's the kind of level that you need to do. And there may have been, say, a Manhattan Project, say by the CIA, to do this, but I don't think that there's good evidence that there's been signals. I don't think there's good evidence that's happened.
Okay.
There's a curious thing about QKD and in the US, in that the US has, compared to the rest of the world, been comparatively uninterested in QKD, at least at governmental level. So it's interesting. Now, why would the CIA, for instance, or the NSA not promote QKD or say very much about it, really? So one could read it in several ways. You can be there's a bit of division in terms of in the crypto community about QKD. I like to think that it is a complementary service that could supplement other mitigations against quantum computers.
Thank you. Now we have a question in the chat from Sean Ashton. How do you envision handling multiple users simultaneously? Traditional networks need very few antennas to handle large user numbers. So far, this looks like each user will need a dedicated laser transmitter receiver.
Yes, no, that's correct. So I think optical communications is possibly in the near term, the only way that QKD can be implemented. Some years ago, Airbus was investigating whether microwaves could be used for QKD. They went dark a couple of years ago. So I know that the researcher on that project basically wasn't able to say anything for a couple of years, because this was obviously very commercially sensitive, whether you could use microwaves to do QKD. I think the jury's still out whether one could go towards, say, microwave or radio distribution. So what we envisage is that, the satellite community is actually going towards optical communications anyway. So there exists the EDRS, it's the European Data Relay Service, which is an optical communications network in space. So to get high-speed data communications between satellites, they actually have optical terminals. This system actually uses an optical terminal to send data from low Earth orbit to geostationary satellites, and then relayed from geostationary satellites back down to the ground. And they use optical comms. There's also optical comms between satellites and the ground. And so companies are now installing fairly large telescopes on the ground to do optical comms with satellites. So QKD could actually be an additional service or additional thing that could bolt on what people are already producing or developing. So I think that's the best way that it could go forward. What we're really looking at trying to do is miniaturize the size of the terminals. So if we can get them down to, say, 10, maybe 15 centimeters in size for the telescope, that could fit on, say, the top of an airline, of an aircraft. So for instance, you could think of an application of secure, autonomous, networked transport systems. So ships, airlines, maybe trucks, lorries, they could all be optically and quantum secured communication. They could be, their communication be secured by quantum key distribution. So, yeah, the thing is that, we would need quite a lot of these new devices, but they're coming anyway.
Okay, thank you very much for that. Sean, hopefully that answered your question. Does anyone else have any questions for Daniel? Okay, Sean says it answered the question perfectly. Thank you. Anyone else going for questions? No? Well, in that case, thank you very much, Daniel. I learned a lot, and I'm very glad that I now have some first-hand information to pass on, or second-hand, to my students. But I will be able to show them the recording of this, which will be much better. So thank you very much for taking the time for this. And it would be nice if we could all just unmute the microphones for a moment to give Daniel a round of applause. And thank you to the audience for turning up. It's I don't know where everyone is from, but I think a fair few people aren't actually from Perth. So it's very interesting to see people turning up. Okay, thank you all. And thank you again, Daniel. I'll be in touch via email.
Yeah, okay, great. We should catch up next time in Perth, if whenever that is possible.
Yes, absolutely. If you do come back to Perth, please do let me know.
Yeah. Okay, great. Thanks.
Okay, thank you all. Bye-bye.